Hi guys, welcome to the lesson of real analysis, and today's class we are going to start a new lecture series on the subject real analysis. So we begin our study of analysis with an investigation of the real number system. So we will see some properties of real number systems, and we will define the properties and in consideration with the properties, we will define the real numbers. So the real number system can be the real number system can be defined or can be completely described, can be described as the complete ordered field, the complete ordered field. So mathematically, we are defining real numbers and we call it the complete ordered field. So now we'll see what actually these words mean, what we mean by complete, what we mean by ordered, and what we mean by field. So I will now talk about these properties. So first of all, we will check the field properties of the field of the real numbers. So field properties of the real numbers of R. So we will uh, denote this real numbers by this R, and every time we will be talking about real numbers, we will write real numbers as R. Okay, so the field property says that R is a abelian group. R is a abelian group, and we will also uh, state these abelian groups and their properties. R is a abelian group with respect to addition and and R minus 0 is abelian with respect to multiplication, and also the distributive law holds. So the distributive law holds. So these three properties, or we can say these three statements are enough for describing a field, distributive law. So now we have 5 axioms for this abelian group with respect to addition, and similarly 5 axioms for abelian group with respect to multiplication, and then we have distributive law. So in total we have 11 axioms that a field need to be satisfied in order to be a field. So the structure that satisfies these properties is called a field. So abelian group with respect to multiplication is simply the a group that is closed under addition. We call it closure property. So it's closed under addition. So this is closure property. It means that if an element belongs to the set, and in fact two elements, if A and B, two elements, any elements belong to the set, then A plus B, that is their sum, also belongs to the set. So this means that the set or the structure is closed under addition. And then we have associative property. So the associative property says that associative property for abelian groups under addition, it says that for all A, B, C belongs to the set A plus B plus C equals A plus B plus C. So this is associative property. Okay, so number 3, we have the existence of identity elements. So in this case, we have, in the case of real numbers, we have 0 as identity with respect to addition. So existence of identity element. Identity which is 0 in the case of the real numbers. And it means that if we add the identity to some number, then it gives the same number. That is, A plus 0 equals to A. And then we have the 4th property, that is existence of inverse, which means that if I add an element to this A, I'll get the identity, that is 0. Okay, so existence of inverse, and number 5 is the commutativity. So if the structure is commutative, which means that if A and B belongs to the set, then A times B equals B times A. This is called commutativity, which in the case of matrices, we can observe that the matrix operation AB is not equals to B times A. Okay, so this is not equal in case of matrices, so we can say that matrices are not commutative. So the commutative property, so these are the 5 properties, and similarly 5 properties with respect to multiplication. These properties are with respect to addition, and then we have with respect to multiplication similar 5 axioms that is closed under multiplication. Closure, call it closure property. A, B belongs to S, then A dot B also belongs to S. Then we have the associative property. Again, the associative property is AB times C equals AB times C in this manner. And then we have the identity element. Identity, that is existence of identity. If I take any element from the set and multiply it with the identity, call it E, which in this case is 1 in the case of real numbers. So I call it E, that is identity. It gives me the number again. Then we have the inverse, existence of the inverse. We can call A times, say, V equals the identity. Or we can also write in this manner A times A inverse, right? So this is identity with respect to multiplication, and then a commutative. Okay, there's a mistake here. This commutativity is in the sense of addition. Mistakenly I write A B equals BA, that is with respect to multiplication. So they are commutative with respect to multiplication. So AB equals BA. Now here we can consider the example of matrices, but not in this case. Not in this case, because the matrix addition A plus B is commutative, but the matrix multiplication is not commutative, right? Okay, so these are the properties, and then we have distributive law. So distributive law should also hold for the field, for the structure that we are calling a field. So for all A, B, C belongs to the set A dot B plus Y equals A, B plus, sorry, it's not Y, it's called C. Because we are considering A, B, and C, so it's AB plus AC. So this is the distributive law. Now, if any structure that follows these axioms, we call it a field. So these 11 properties are satisfied by a structure, then we call it a field. And for real numbers, we can check that these uh, properties are satisfied by the real numbers. So we can see that if we take any real number, let it start with the first property, that is closed under addition. Here we can see that if we take any number from the real numbers and we add them, any two numbers, and we add them, we know that the number that we get it will be from the real numbers. For instance, if I take A equals 2.95 and B equals negative 36 or 37.33 arbitrary, if we add them, so this will be negative 37.33 plus 2.95, which will be a number, and it will be again a real number. It will be from a real number, right? So we can see that if you take any two numbers from the structure of real numbers, we are going to sum up, then we are going to get a number that will be also from the structure of the real numbers. And then associative property also holds any number. If we sum up in this manner, we will get this thing, or we can just equate and check whether this property holds, and yes, it does hold. And then existence of identity, we have a plus 0 equals A. And again, if we add 0 to any number from the real numbers, we are going to get the same number. And for the inverse property, we have inverse of every element. For instance, if I take negative 3.952, then I have 3.952 as well, positive 3.952. That if I add this to this number, I'm going to get the identity, which is 0. So this property is also satisfied. And then if I check for the third property, that is commutativity, and the commutativity also holds the positions of these two elements doesn't matter. If I add A plus B or I add B plus A, then I'm going to get the same thing, right? Okay, so the order doesn't matter. This is commutativity. And then for with respect to multiplication, yes, it's closed under multiplication. If I take any two arbitrary numbers from R and I multiply them, I will get a number that will be from the R, from the real numbers. Again, associativity, yes, it holds these. Again, the order doesn't matter for associativity, right? In case of the real numbers. And then we have the identity element. And yes, we have the identity element, that is 1. In the case of real numbers, if I multiply any number with 1, I'm going to get the same number. And then for the inverse, and yes, inverse exists. Take any number, for instance, 3.6928, or say 5.6928, then yes, I have the number 1 over 5.6928. That is also, that belongs to the real number. So this is its inverse, and if I multiply this number with this number, I'm going to get the identity element. So that's called the inverse property, and inverse exists in the real numbers. Again, the commutativity. For commutativity, the order doesn't matter for real numbers, as we have seen in the example of matrices where it matters, but it doesn't matter in the case of real numbers. Take any two real numbers, multiply both of them in any order, you will get the same result. And again, the distributive law, this also holds for the real numbers. So I take any three real numbers, and like for instance, if I take 2.1, A equals 2.1, B equals minus 2.7, and C equals 39.5, and then apply this rule, this and this rule to these numbers, I will get the same result. So we conclude that the real number possess the field properties, so it's a field. And then we have some other structures like natural numbers, which is not a field. You can check that it does not hold some properties, like it does not have inverse element. For example, we know that real numbers are 1, 2, 3, 4, 5 to infinity. And if I take any number, for instance 2, so with which number I can multiply 2 to get the identity? That is, what is the inverse of 2 in this group, in this structure? There is no inverse. That means I need 1 over 2, but 1 over 2 is not present in the structure of the natural numbers. So natural numbers does not possess the property of field, so it's not a field structure. Again, if we talk about the integers, so integers, we can check for the properties. If we take any number, we know that integers are from negative infinity, and say -3, -2, -1, 0, 1, 2, 3 to positive infinity. And if we check that properties that close under addition, yes, it's close under addition. Is associative, yes, it's associative. And if we check that whether it has the identity element, yes, it has the identity element, that is 0. It has the inverse element in multiplication, yes, it has. If I take any number from Z, for example 3, then I have -3 as well. So these possess field, it's a group with respect, abelian group, in fact, with respect to addition. And then if we check for multiplication, with respect to multiplication, what can we observe here? So where does it fails to be the field? So if I ask about the multiplicative inverse, for instance, I take a number 29. So where is the multiplicative inverse of this number? With which number I should multiply this to get the identity, that is 1. So I have no number because I need 1 over 29, and 1 over 29 does not belongs to the set of integers. So this is not a field. And then again, rational numbers. Rational numbers are x such that, or we can write it as p over q such that p and q belongs to the integers. X equals p over q. So every element is of the form p over q, and p over q belong to the integers, right? Where q cannot be equals to 0. So this is the definition of the rational numbers. So for rational numbers, we can check that they satisfy all the properties of the field. So they are a field. So rational numbers, the structure of the rational number is a field. Okay, likewise, we can check for other numbers as well, other groups, other structures, other sets. We can check whether they possess the field properties or not. So we conclude that set of real numbers, it's a field. Now the second property that we call it as the order complete, order properties of R. Okay, order properties of R. So what actually are the order properties of R? Now we will check about order properties of R. So number one property is trichotomy. It's called trichotomy. Trichotomy. So trichotomy says that if AB belongs to R, then exactly one of the following inequalities hold. Okay, so if A and B belongs to the set of real numbers, then this will happen. Either A will be less than B, or A will be equals to B, or A will be greater than B. There is no other choice. There is no other choice other than this thing, these three choices, right? So either A will be less than B, or A will be equal to B, or A will be greater than B. This is the first property, that is trichotomy property. Then we have the transitive property. So we have transitive property. Okay, so the transitive property says that if ABC belongs to R, if ABC belongs to the set of real numbers, that is R, then A is less than B and B is less than C simply implies that A is less than C. So it transits, right? So A is less than B, fine. Then B is less than C. Then ultimately A is less than C because A is less than B and B is less than C. So then this thing implies that A is less than C. And then the third property is Archimedean property. Archimedean property. Okay, so the Archimedean property, it says that very important property that if A belongs to the set of real numbers, then there exists a positive integer. I will call it as Z plus. There exists a positive integer that is Z plus, because Z is the notation for the integers, and when I apply plus sign, then it means that it's from the positive integers such that n is greater than A. So go as far as you like, as bigger as you like, but in the real numbers, in the structure of real numbers, you can take any element as far as you like, as bigger as you like, but you will get an integer n which will be bigger than A. Okay. And then the fourth property is the density property. Okay, so density property says that if A belongs to R, that is a set of real numbers, and B belongs to R, okay, two elements A, B belongs to R, and A is less than B, then there is a rational number, is a rational. There is a rational Y such that A, okay, rational Y such that A is less than X less than B, A is less than Y less than B. Okay, sorry, one mistake here. So and A is less than B, then there is a rational number and rational number X, and or call it like this, X belongs to Q, X belongs to Q, X belongs to Q, and a number Y belongs to Q complement, that is irrational numbers, such that A is less than X is less than B, A is less than Y less than B. So it simply tells that between any two real numbers, as close as you think, any two real numbers, there exists a rational and irrational number in between them. So it's amazing, but this is called the density property. Take any of the two numbers as close as you can think, but there exists a rational and irrational number between them. What does it mean? Simply, if I can give an example, for instance, if I suppose that 1 and 2, let A equals 1 and B equals 2, and I can easily show that in fact, there are infinitely many rational and irrational numbers between these two. But if I want to find one, so I can say x equals uh 3/2. It's a irrational number. Y equals the square root of 2. This is an irrational number. This is a rational number. Since 3/2 is between 1 and 2, and again square root of 2 is between 1 and 2. So we see here. Okay, this is called the density property. Okay, so there's a remark here that it's a remark that Archimedean property is sometimes expressed. Archimedean property. Archimedean is sometimes expressed in a way that for all positive real numbers, say it's R positive, there is a positive integer, there exists a positive integer, call it Z plus, it's from Z plus. Okay, not like this. We can write it like this: for all, or you can say for any positive, for any positive real number A, say A, and call it as it belongs to the real number R, positive real number R positive, there exists and belongs to the positive integers such that 1/n is less than A. Okay, so we can say that there is always a number bigger than 1/n, no matter how far you are going. So n is actually equals to 1, 2, 3, 4, 5, and it's like this. Because n belongs to the integers and positive integers. So positive integers are the natural numbers. Okay, so these are the order, order properties of R. And then we have the completeness property of the field of real numbers. So we'll talk about the completeness properties, the last property, completeness property. So we will end our discussion here, the completeness property of R. So the completeness property says that every non-empty, an ordered field, an ordered field F is complete. An ordered field F is complete if it satisfies the completeness property. Now, what actually is completeness property? Okay, so we call a field, a order field, as complete if it satisfies the completeness property. So the completeness property says that the property, I am making it a star, it says that every non-empty subset of F that has F is field here, F is for the field that has an upper bound, that has an upper bound. Okay, so it has an upper bound that has an upper bound in F. So it means that the upper bound should be from the universe of the field that you are considering, right? And we will also see some examples, complete and non-complete structures, and it will be more simple for you, more understandable. So upper bound in F. Okay, so has a least upper bound in F. Okay, every non-empty subset of F that has an upper bound in F has a least upper bound in F, has a least upper bound in F. So this is the completeness property, upper bound in F. Okay, so it should have the least upper bound in F. And caution is that recall that the word has here that does not mean contains. Okay, it does not mean that it contains. The supremum of A need not to be a member of the set, but it should be the member of the universe from which you are from which that set has been taken. Okay. Okay, so any complete ordered field is called Archimedean field, and then we can see that the field of real number is complete ordered field. So R, think about R, take any interval in the R, for instance 2, 3, like this, 2 and 3, and we can find the upper bound, that is 3. Okay, so the least upper bound, we'll talk about these upper bounds and lower bounds, what are upper bounds and lower bounds. So we'll talk in the next lesson, but for instance, for the understanding right now, it has the upper bound 3, and it has infinitely many upper bounds, but the least upper bound it has is 3. All right, and it is contained in the set, but it doesn't matter that if it is in this set or not. Call it set A. Set A is basically a subset of R, so it's contained in R. Okay, so set A is contained in R, so it's a subset of R. And now if we think about the lower bound, that is greatest lower bound, it is 2 right here, 2, but it is not in the set. But doesn't matter, we know that 2 belongs to R because R is the universe. R in this case is our universe. So this 2, that is the greatest lower bound, it is from the universe, right, in R. So this is the least upper bound. So the least upper bound is present in the set. Sorry, it's greatest lower bound, not the least upper bound. Okay, so its greatest lower bound is 2 and least upper bound is 3. All right, now think about the set. It's an example that if we have a set that is X squared, X belongs to rational numbers such that X squared is less than 2. Okay, so in this case, X belongs to the rational numbers, but rational numbers of a kind whose square is less than 2. If I want to write in this manner, I can write P over Q. Okay, so it represents the rational number P over Q such that P and Q belongs to the integers, and Q not equals to 0, and X is squared, or P over Q whole squared, we can write in this manner as well, P over Q whole squared is less than 2. So we can see that this set has the upper bound, that is this 2 here, that set has the upper bound. But if we want to find that is the least upper bound, if we want to find the least upper bound, so there are many numbers that are lesser than whose square in rational numbers is lesser than 2, but we cannot actually find that number, right? So we cannot find the least upper bound for this problem, and we know that the upper bound here, which we have this 2, so it simply means that if I want to find P over Q for this, then it's like square root of 2. So where this square root of 2 does not belong to the set or the universe of rational numbers. So it is not from the universe of the rational numbers. So it's not from the set, so we cannot find the least upper bound for this problem. So we see that this Q is not actually the not complete, right? So it means that there are gaps in the rational numbers. It is not complete, but in the real numbers, there are no gaps. So because in rational numbers, there are in between two rational numbers, there are infinitely many irrational numbers, and between two irrational numbers, there are infinitely many rational numbers. So that's why these structures are not complete, but the structure of R is complete. Okay, so that's all for today, but in the next lesson, then we will talk about some more properties and that are important for the subject of analysis. And we will see some examples as well. We'll solve some inequalities as well. Okay, thank you.